Hello and welcome to Joey's AP Precalculus. This is lesson 1.8, rational functions and zeros. Today we have one lesson objective of determine the zeros of rational functions. We have briefly gone over this concept by looking at how to find x-intercepts of rational functions in the previous lesson. Today we'll be looking more into how to determine the real zeros of rational functions. So first of all, what are real zeros of rational function? The real zeros of a rational function can be found by determining the real zeros of the numerator of the rational function. Essentially, as we have learned in the previous lessons, rational functions are essentially a combination of two polynomial expressions in a form of fraction. So the denominator is a polynomial function or an expression, and the denominator is also a polynomial expression. So both the numerator and denominator is an expression. I hope you guys all know about how fractions can be zeros. Whenever we have a zero in the numerator, regardless of what value we have on the denominator, that equals zero. So essentially, if we were to find the zeros of a rational function, we can essentially just find the real zeros of the numerator. However, this is an important thing. If the real zeros of the numerator can also make the denominator equal to zero, the entire function value would be undefined. Therefore, such real zeros are not zeros. So whenever we have a zero in the numerator, it normally always equals to zero, but there is only one instance where that is not true. When the denominator is also equal to zero, when we have 0 over 0, that is undefined. The reason why is essentially you can't really divide anything with 0. That's undefined. So make sure to determine that whenever you found a real zero of the numerator, make sure to plug that into the denominator and confirm if the denominator would equal to 0 or not. If it does not equal to 0, that's a real zero. If it does equal to 0, that function value would be undefined, so that is not a real zero of the rational function. So let's look at this example we have here. We have f of x is equal to x squared plus 10x plus 24 over x squared plus x minus 12. We first can find the real zeros of numerator by factorizing it, right? So if we factor it, if we factorize it, we will be getting x plus 6 times x plus 4, and we found that the zeros of the numerator are x is equal to -6 and x is equal to -4. We can confirm if these are actual zeros of the entire rational function by plugging those values into the denominator. If you were to plug in -6 into the expression of the denominator, we will be getting 18, which is good. However, if you were to plug in -4 into the denominator, we will be getting 0 as our function value, which is bad. Why? Because that would be undefined. Because -4 would make the entire rational function undefined because it would be 0 over 0. Therefore, we can conclude that because x is equal to -4 makes the denominator 0, x equals 4 is not a 0 of f of x. Therefore, x is equal to -6 is the only 0 of the function above. Now let's also look into positive and negative function values of the polynomial function. So in order to determine the overall graph shape, a useful method that can be used is determining intervals of which a graph is positive or negative. Possible intervals that can indicate positive or negative function values can be found using the zeros of both the denominator and the numerator. So, for instance, if x is equal to -3 and x is equal to 2 are zeros of the numerator, and if x is equal to 2 and x is equal to 4 are zeros of the denominator, we can set our intervals with these values. Using the value x is equal to -3 and x is equal to 2, we can have this interval and this interval. Using these two, or this as well, we can frame different intervals, and essentially by plugging in test points, I'm going to explain how we do that in a moment, into these intervals, we can determine if a function is positive or negative in a certain interval. So what I mean by this is if you were to determine if a function is positive or negative, what that means is that if a function is above the x-axis, that is positive. If a function is, I spelled that wrong. If a function is below the x-axis, that region is negative. So the best way to determine if a function is above or below the x-axis is through this method. So first, you're going to find the zeros of the denominator and the zeros of the numerator. So we found that as -6, -4, and -4, -3. These are essentially our hints of possible intervals where the function switches from negative to positive or vice versa. So using these four zeros of both the numerator and the denominator, we can set intervals. So because -6 is the smallest number we have, our first interval would be x is less than -6. Our second smallest zero is -4. So using -6 and -4, we can set our second interval like this. And we can set our third interval using the fact that +3 is the greatest zero that we have. We can set our third interval as with -4 and 3, and we can set our last interval with only 3. The reason why we're setting these intervals is because the point where the function switches from positive to negative or negative to positive are essentially the zeros of denominator or numerator. So we're essentially having intervals to see, there we go, to see if an interval is positive or negative, or if the function is negative or positive. So how we're going to work this out is we're going to let's think of one test point that is less than -6. If we think of something, that can be something like x is equal to -6. Sorry, x is equal to -7, x is equal to -10. These are all test points that are less than -6. Then we're going to plug these points back into our function. If we do so, we will be getting that f of x is greater than 0. So by plugging in test points, we can conclude that in this first interval we have of x is smaller than -6, our corresponding function values would be positive. We can do the same thing for the rest of the things. So our second interval, we can set our test point as -5, and if we plug in, we'll get a negative value. So we can conclude that in that interval, our function values are negative. We can do the same thing with the third interval. What is a test point that is in between -4 and 3? It can be something like 0, right? So if we plug in 0 to our function, we will be getting a negative function value. Great. Let's test out our final interval as well. Let's think of a test point that is greater than 3. It's something like 4 or 5, right? Then let's plug in 4 or 5 into our function here. If we get a positive value, that means that in this entire interval of x is greater than 3, the entire function value would be positive. So essentially, using this method, we can determine if intervals of functions are positive or negative, and when those changes from positive to negative or vice versa happens. Great. Let's try some example questions that are highly similar to AP style questions. So our first example is this. Find real zeros of the following rational function. So first of all, let's factorize them. Okay, so we can factorize them as x minus 3 times x plus 1. And we can factorize the denominator as x minus 5 times x plus 1. If you are not proficient of the process of factorization, I highly recommend reviewing Algebra 2, because factorization is an important skill to have in AP Precalculus. I will not be going over them in detail, so yeah, I'll expect that you are proficient with how to factorize polynomial expressions or quadratic expressions. So we factorize them like this. Yeah, we can give it a double check by using the FOIL method to expand them. Then we'll be getting this. So great. So first of all, the method of finding real zeros, we're first finding the real zeros of the numerator. So if we take a look at the numerator here, we can determine that the numerator has zeros at x is equal to 3 and x is equal to -1. We can also find a denominator 0 now by looking at the denominator's expression. We can determine that the denominator has zeros at x is equal to 5 and x is equal to -1. So essentially, our zeros of the entire rational function can be x is equal to 3 and x is equal to -1. But as I told you, we have to check that the numerator 0 does not overlap with the denominator 0, because in that case, we have 0 over 0, which makes the entire function value undefined. So if we take a look, x is equal to 3 is absolutely correct, because that 0 does not occur in the denominator. However, x is equal to -1 does occur as the denominator 0. So that is not a 0 of the entire rational function. Therefore, x is equal to -3 is the only 0 of this entire rational function. Great. Let's look at example 2. Find the real zeros of the following rational function. You may use a graphing calculator. Great. Let's kind of take out a graphing calculator together, and let's go through this together. So let's open your TI-84. I'll be using TI-84 throughout this video in the textbook. If you have TI-Inspired, that is also okay, or TI-83, that is okay, but I will not be going over how to use them in detail. So let's open TI-84 and let's click y equal and input this fraction. How can you input this? You can simply just enter the numerator first and click the division sign and input the numerator. That's the easiest method, I think. So if I'll give you a moment to input this rational function in your TI-84. Great. Now the next thing we're gonna do is we're essentially real zeros are equivalent as x-intercepts when you graph them, right? We learned this in our previous lesson. I think it was lesson 1.1. So essentially, let's just graph this. Let's click the graph button. If your graph isn't if it's like scaled wrong or if it's not showing up correctly, you can click zoom and you can scroll down and click 0 zoom fit. That's for TI-84. So okay, now we can kind of see the entire graph shape, but we exactly don't know where x-intercepts occur. So we're going to ask the calculator to do that for us. We're going to click second and then click trace, which would lead us to calculate function. And then we're going to scroll down to intersect, and we're going to find x-intercept. But my bad, I forgot that we have to add another equation. So let's go back to y equals, and let's add 0 as at y2. So our y1 will be this entire rational function, and our y2 would be y2 equals 0. Let's go back to graph, and let's go back to second trace, which will lead us to calculate. And let's click intersect, which is at 5. And then we're gonna move our cursor closer to our intersection points. And then we're gonna click enter, enter, enter after our cursor is moved to our suspected intersection place. Then the calculator would give us this intersection x is equal to -2, y is equal to 0. Let's do the same thing. Let's go to second trace, intersect, and let's go to our second x-intercept suspected point, and let's just click enter multiple times. Then we get our second intersection point. as x is equal to -1, y is equal to 0. Essentially, if you were to zoom in and look, you can zoom in by clicking zoom and then to zoom in. The graph only has 2 suspected x-intercepts. So that's what we found, which is great because that is our correct answer. So you can conclude that there are 2 real zeros of this rational function. X is equal to -2 and x is equal to -1. Questions 3 and 4 are similar. So I'll only go over question 3. So I told you that we can use intervals to find regions where the function can be positive or negative. So let's first find the numerator 0 and the denominator 0. So our numerator zeros are x is equal to 3, x is equal to -4, and x is equal to 2. Our denominator zeros are x is equal to 2 and x is equal to -1. So using these values, we can set our intervals. Our first interval can be used using this. So we can have x is smaller than -4. And our second interval can be framed using x is equal to -4 and x is equal to -1, as -4 is greater than, x is greater than -4 and less than -1. Our third interval can be made using -1 and 2. So we will be having -1 is greater than x is less than 2. And our fourth interval would be using x is equal to 2 and x is equal to 3, as x is greater than 2 and x is less than 3. And our fifth interval would be x is greater than 3. So I'm going to use this region here to use test points. So our first interval's test point can be x is equal to -5, because -5 is a value that is less than -4. So what I'm going to do is I'm going to plug in -5 into this entire fraction and determine what value we get out of that process. This is a time-consuming process, but it is a good practice to kind of be able to know what values come out when we plug in test points. So if we were to plug in -5, we will be getting -2. So it is a negative value. So our first region, our first interval of x is less than -4, by plugging the test point of x is equal to -5, we can conclude that the first interval is negative. Let's test out the second interval. For second interval, we can plug in x is equal to 0. If you were to plug in x is equal to 0, we will be getting y is equal to -12. You're essentially plugging in x is equal to 0 to here and see what value you get. That's essentially -3 times 4 times -2 over -2 times 1. So we'll be getting 24 over -2. So that's essentially -12. So yeah, our second interval is also negative. Sorry, my bad. That should be our third interval. Because x is equal to 0 is not in this inequality. It's in the third interval inequality. So for second one, let's actually do something like x is equal to -2. If we were to plug in x is equal to -2, that's going to give us 10. You can try it out if you're curious. That's a positive value. What about our fourth interval? We can plug in x is equal to 2.5 as our test point. And if we do so, we'll get something close to y is equal to negative 0.929. That is also a negative value. For our fifth interval, let's plug in x is equal to 4. If we do so, we'll be getting y is equal to 8/5, which is a positive value. So by going through all the test points, we can conclude that the function is negative in these intervals, right? So those are intervals of 1, 3, and 4. So we can write our answer as, I'm going to erase this all. The function is negative in the interval of we can write this in an interval notation like this, and essentially this union unit means or. So yeah, that would be a completely correct answer of illustrating the interval of which the function is negative. So great, we have looked into different concepts of how to find zeros of rational functions, and using the information of the denominator 0 and the numerator 0, we also learned how to find which intervals the function is positive or negative. Hope you had a fun time learning this concept, and as always, if you have any questions, feel free to email me or comment below so I can answer any questions you have. Thanks so much for watching.